Just in time. We're going to do some linear algebra review. Yeah. All right, this is the Tutor Wizard. This is Willa. I'm Adrian. Please subscribe. You'll get notifications for these series for your review problems and many more special topics, other math classes, etc., etc. What we're doing here is, this is going to be, I'm going to put up a whole bunch of videos, hopefully 10 or 15. We're going to do 2 or 3 problems at a time so that you can watch and prepare for the final exam for Math 120. The first question I'm going to do is this one, and then it will give you a rough guideline also as to the types of problems that you can expect on, in general, a linear algebra final exam, or more importantly, specifically for my classes for this COVID scenario for Math 120. So we're going to do 2 or 3 problems at a time. For the first video, what we're going to do is, number 1, I'm going to have to erase the whole thing. So here it is right now. Take a mental image or rewind every time you can't forget. Flip back on the page when you have it on paper. Go back to the question. What is the definition? Look these types of things up. If you can't remember, as soon as there's something in here that you're like, normal vector, yeah, go look in the book and find out what that is. I'll explain what the normal vector is. We have a plane P. It has the general equation, this. A is a freebie. I already see it, 1, 1, minus 1. But okay, what does A say? It says find the normal vector for P. The normal vector is the numbers or the coefficients standing in front of x, y, z in the general equation. 1, 1, negative 1. That's the normal vector. It's already there. B says, oh, we'll do that in detail in a second. B is, it asks us a question now. Question mark. Is P parallel to this line? If it is parallel, C says, Mark never lets you get away with it. You're not done with this. You're like, oh, yes or no. Even if it is, he's got more work in either scenario. If they are parallel, if it's yes parallel, find the distance between them. Ha, ha, ha. More work. If they're not, find their intersection point. Either way, we can make you do something else, regardless of what the question of A and B is. This is a classic example of what we can do with lines and planes. Remember also, before we start, a plane is a 2-dimensional object inside 3 space. A line is a 1-dimensional object in 3 space. A line has a vector in the direction of it. A plane has an equation which describes a vector n perpendicular. So when the object plane is parallel, like in my picture, to the object L, the vectors representing them are orthogonal, which means it should be Pavlovian at this stage. It means their dot product is 0. Their dot product is 0. So if, for this one, before I erase it, and I need the information, this is all I need from this now too. The algebraic avatars of these guys, the plane in its general avatar, and the line in its which, that's correct, parametric avatar, because there's a parameter t, and that's describing these 2 things. What does that information give me? This gives me the normal vector immediately, and in here that gives me a point and a vector in the direction of my line. Let's do the problem. Okay, so here's the avatars, or one of the avatars of each of these objects I've been given. Here's the general avatar of the plane, and the parametric avatar of the line. Equations, they call them. I call them avatars. There's many of them. Usually you like the geometric ones. There he is. What do I need from this to answer A? A says find a normal equation or a normal vector to this. The normal vector, A, why did A go so low? A, B, C. In the general equation, they say you see what we're doing? In theory, we say this is the general equation of a plane. And it says, in that scenario, A, B, C, that gives me the normal vector. The coefficients standing in front of x, y, z are the coordinates of the normal vector. So in our case, what is n? 1, 1, minus 1. A was a freebie. If you didn't like that, oh my goodness, you're not going to like B and C. There's the normal vector. All I need, and I'm trying to parse out what you need for the next steps. All you need to compare the line and the plane are the normal vector and the vector in the direction of the line. So A was just getting one of those pieces for you. B should have been, what's the vector in the direction of the line? 2, 1, 1. The guy standing in front of the parameter in this, because that's what the avatar tells me in parametric form. So B asks me, now that I have N, B asks me, are the line and the plane parallel? So there's the objects, the two-dimensional object plane. Here's the one-dimensional object line. They have vectors in their directions, but V for a line is in the direction of that guy. And P in the general form or the normal equations are going to be N is perpendicular to that object. So if I ask the question, is P parallel to L? That says the vector in the direction of L will be orthogonal to the normal vector to P. Let's check that. How do I check that? Well, I need V. Who's V? V is 2, 1, 1. And what do I get? Not 0, 2. When are these guys orthogonal? Pavlovian. I check their dot product if and only if they're orthogonal. So N is orthogonal to V if and only if N dot V is 0. But we're going to check this direction because I have the two vectors. I can check their dot product and that'll tell me whether they're orthogonal. That's what I'm using. This. So check this. N dot V is equal to, I erased them. They're here. I've got them. Haha, they're there the whole time. This is 1, 1, negative 1. When I'm lazy and I know what I'm doing, I'm not even writing any of that pre-down for myself. I'm just going 1, 1, minus 1 there. Dot product with 2, 1, 1, which is by definition 1 times 2 plus 1 times 1 plus negative 1 times 1. Cancel, cancel, which is equal to 2, which is not 0. Therefore, N dot product V is not equal to 0, which means N is not orthogonal to V, which says P is not parallel to L. That was my lazy way of saying that, but they're not parallel. Good. Either way, Mark doesn't let you rest. No rest for the wicked. You now have to do part B of part C, or part II of part C, the second part. They were not parallel, so I don't have to find, there is no distance between them. What he meant by that was there had to be some distance between them if they were parallel. That's not our case anymore. They have to intersect is what's happening. So now what we're doing is, this is L, and we have to find this. Ooh, find X. There, yeah, that's not what they meant by that. They meant find the coordinates explicitly for that point. Remember also, when I do this last step, there's a parameter. I'm going to have to find the parameter for when they intersect. The parameter T is a finite scalar. It is not the three-dimensional point of intersection of the plane. This is most often the common mistake. You find the parameter T for when that happens, and then you say, here's the intersection point, T equals 1/2. It's like, no, that's the parameter at which it happens. This will be the three-dimensional point in 3 space for when they intersect right there. It's got 3 coordinates, X naught, Y naught, Z naught, which happens at T naught, which we're going to find. So first we're going to find this, then we'll find the point of intersection. Let's do that. C, the plane was X plus Y minus Z plus 1 equals 0. My line is X, Y, Z equals 1 plus 2T equals 2 plus T equals T is my line. And now it wanted to know, we've deduced the fact that they are not parallel, so they must intersect regardless of whether they're perpendicular or parallel. He was nice and he didn't ask if they're perpendicular. We didn't check. When would that be? If they're scalar multiples of each other. Is 1, 1 minus 1 a scalar multiple of 2, 1, 1? No. So they're not perpendicular either. They're oblique. But this line and plane now are oblique, which means they don't intersect at 90 degrees. They intersect at some other angle, but they definitely do have an intersection point, and we're about to find it. Notice how every time I try to describe that to you or do something, what am I doing? Following Mark's description, or I get like an email saying, do it, draw a picture. Draw a picture for yourself. It helps, trust me. I don't want to get yelled at again. I feel shame. What are we going to do? Step one, I'm going to, this is just like in calculus, I say, when does sine equal x? They're closer and closer near zero, but they're not equal to each other. At zero, they're equal to each other. That means their equations equal each other. I would set up x equals sine x. It's like, oh, I can't solve. When do you solve it? Luckily, I can find one. Can you show that this function f of x equals sine x minus x has exactly one real root? Now I'm talking about too much calculus. We're doing linear algebra, but I could show there's a unique solution to this. What is it? 0 equals 0. Sine of 0 is 0, so the only solution is 0. And then they're never going to intersect again. My point being is, when do I find when they intersect? I set their equations equal to each other in calculus. We're going to do something similar in linear algebra. This one and this one, at this point, they're the same. This point in space, x naught, y naught, z naught, is in a point in space, but it's simultaneously on the line L and on the plane. It's the only point that's on both of them, but it's their intersection point. So I'm going to put this in here, because this line has to satisfy the plane's equation at that point, and then I can find the parameter t. I'll have one equation and one unknown. Solve for t, but that's not the point. That will give me the point. I'll find the t dot when it happens, and then when I do that, that will give me the point by putting it back into the parametric equations of the line. Step one, find the parameter by putting this into here. X is 1 plus 2t, plus y is 2 plus t, minus z is t plus 1. That will give me t. So 1, I plug the line into the plane because they're equal at that point. This says 1 plus 2t, x plus y is 2 plus t, minus z is t plus 1 equals 0. Solve for t. This is one equation and one unknown. This is a 1-by-1 linear system. I think we can do this. This is what Gauss systematically does with Gauss-Jordan elimination. You eliminate till you have one equation and one unknown at the bottom, and then you backtrack up. You're going to have to do this on the final exam too. What do I have? 1 plus 2t plus 2 plus t minus t plus 1. I be careful and don't skip steps. Gone, gone. What do I get? I've got 2t plus 4 equals 0, which says 2t equals negative 4, which says t equals negative 4 over 2, which is negative 2. T naught is negative 2. Again, if I made a mistake, okay, I'll give myself a little mini, let's make it red, oh bad boy, because you got the number wrong slightly. That's not what I'm looking for on the exam per se. If you made a slight calculation error, yes, you may see me do this. I'm going to have to watch them to double check that I didn't make any mistakes. But assuming I didn't make any mistakes, or even if I did, I have the procedure of what's supposed to be going on correctly. So if there's a little error, okay, so be it. There's a little error. But for this one, I now have t naught I claim is negative 2. Let's find the point of intersection based on that. That tells me I put t naught in here to get the three-dimensional point of intersection. Once I have t naught 2, t naught equals negative 2 goes into the equation of L. That says x, y, z is equal to. And this is where we're finding the knots now. X naught is equal to 1 plus 2t, which is negative 2. And y naught is 2 plus t, which is negative 2. And z naught is negative 2. So this gives me negative 4 plus 1, which says our three-dimensional point x naught, y naught, z naught is equal to negative 3, 0, negative 2 is the point of intersection of that line and that plane. Good. Question 2. Okay, number 2, what we're going to do is, I have a 3x3 matrix. Basically what I'm parsing out here is the steps in my mind that I do to most efficiently compute the inverse of a matrix. Step 1 is essentially check that the determinant is not 0. If it is 0, I don't have to do anything. Yay, I say it doesn't exist, no more work. Good. That's what I'm wanting on an exam. Don't hold your breath. It's not what I'm going to do. You're going to have to compute at least one inverse. We have 2 methods. We have the row reduction method, which I'll do in the next video or some other video. But for now, I'm going to use cofactor method. This is extremely useful. You have to know how to do cofactors to compute determinants. Determinants are several different ways to compute inverses. And then we use Cramer's rule to use ratios of determinants to solve linear systems and inverses to solve linear systems. So This is not going away. This is definitely going to be on the final exam in any linear algebra class, I would hope, in some guise or another. How do I do this? All I need is A. Remember, again, I'm going to compute the determinant by cofactor expansion along row 1. This is A11, A12, A13. I already have the A's. I need theCij's. That's what it tells you. Compute C11, C12, and C13, and then I can compute the determinant by cofactor expansion along row 1 following Louis Augustin Cauchy. Let's do that. C11 is negative 1 to the 1 plus 1, M11, which is M11, which is equal to what? Obtained by blocking off row 1 and column 1. 2, 1, 1, 0, which is 0 minus 1, which is minus 1. C12 is equal to negative 1 to the 1 plus 2, M12, which is negative M12, which is equal to negative, obtained by blocking off row 1 and column 1, which is the Roman cross, which is 0, 1, negative 1, 1, 0, 1, negative 1, 1, 0. Either way, it would have killed it, luckily. 0, oh, we got minus, minus, minus is minus, minus 1 is positive 1, and then we got a negative, so we get negative 1. This is where I'm going to have to check after, because did you do that? C13 is equal to negative 1 to the 1 plus 3, M13, which is M13, which is equal to the 2 by 2 determinant obtained by blocking off row 1 and column 3, 0, 2, negative 1, 1, which is equal to 0, minus, minus 2, which is 2. All I needed was those values. Oh, was that a negative? Yes. Negative 1, 2. From those, the determinant of A is equal to A11, C11 plus A12, C12 plus A13, C13, which is now equal to magic A11, A12, A13. Color coding helps your memory. If you're writing this down, regardless of whether you do it, you should do this for yourself as you watch videos or do these things. Pause, write it down, make your muscle memory do everything. I'm finding the A's from the matrix originally. My mind already knows they're coming from the matrix. I'm not worried about the A's. You're like, where's the A's coming from? Where's the C's? I've got the A's. It's the C's I should be worried about. I just built them. I just put everything in there. Numbers, numbers, numbers. No fractions if they didn't put fractions in here also. Notice why I like this. A11 is negative 1 times C11, which is negative 1, plus A12, which is 1 times C12, which is negative 1, plus A13, which is 1, plus C12, which is 2. Even if you want, double down on that. This one, and this one is minus 1, 1, 1 is where I got those from. The matrix originally. That gives me cancel, cancel equals 2, which is not 0. Otherwise, we didn't have any work to do. So this says the determinant of A is not 0. Therefore, we can find the inverse and we go to step B and compute all the other cofactors. Remember, we need to find the inverse. The inverse is now going to be 1 over determinant times the adjoint, which is the cofactor matrix transpose. So I need all 9 cofactors. So don't erase those ones. We'll move them over. I also keep what I need. I need the determinant because I need 1 over the determinant. The formula now in my head is, and you're going to have to bring this in, you memorize it and memorize it as soon as you get in the exam, or I give you one, or in COVID, don't worry, it's open book and you get 6 hours, I guess. Bah, bah, bah. The formula is, what do you want me to do about that? I don't know. 1 over the determinant adjoint of A. I don't even like the big machinery. If you're only going to take this class and you don't want to take 225 and you don't really care, C transposed, who's C? The cofactor guys. That's how I memorize what the inverse is. 1 over the number, which has to be non-zero, so I can do it, times this cofactor business. I need the other 6 cofactors. Let's do that. C21 is equal to negative 1 to the 2 plus 1, M21, which is negative M21, which is negative times. Now we're going to block off row 2 and column 1. So 1, 1, 1, 0, which gives me, oh, I drew that too close, 0 minus 1, which is positive 1. C22 is negative 1 to the 2 plus 2, M22, which is M22, which is equal to the 2 by 2 determinant by blocking off the Greek cross now this time. This one and this one, which is going to be negative 1, 1, negative 1, 0, which is 0 minus minus 1, which is 1. C23 is negative 1 to the 2 plus 3 M23, which is equal to negative M23, which is negative times the 2 by 2 determinant of blocking off row 2 and column 3, which is negative 1, 1, negative 1, 1, which is 0 because they're multiples of each other, those two rows gone. C31 is equal to negative 1 to the 3 plus 1, M31, which is M31, which is equal to the 2 by 2 determinant by blocking off row 3 and column 1, 1, 1, 2, 1, which gives me 1 minus 2, which is negative 1. C32 is negative 1 to the 3 plus 2, which is negative M32, which is negative 2 by 2 determinant. Negative 1, 1, 0, 1. Negative 1 gives me positive 1. C33 is negative 1 to the 3 plus 3, M33, which is M33, which is this, which is this guy, negative 1, 1, 0, 2, which is negative 2. We'll see if I got those right. Don't go so fast. Take a breath in between when you calculate and make sure you get the numbers right. I just want to crush them all out. I've done these before. Up to calculation and little errors in your brain. If you write this on the page, I'm going to give you a big fat check mark anyways, because even if there's an error in one of these guys, I see you know what you're doing clearly. This is the regurgitated definition of what all the cofactors are. Now I've got them. What do I need with that? I need to start using the eraser. Are these things safe for your skin? I don't know. So I also need the cofactor matrix. That's now C11, negative 1, C12, negative 1, 2. Row 2 is going to be 1, 1, 0, and row 3 is going to be negative 1, 1, negative 2. This is the matrix of cofactors of A. And that's not quite what I need. I need that thing transposed. So that will be negative 1, 1, negative 1, negative 1, 1, 1, 2, 0, negative 2. That tells me that A minus 1 is equal to 1 over the determinant of A cofactor matrix transposed, which is now equal to 1 over a number, scalar multiplication times a matrix, which is negative 1, 1, negative 1, negative 1, 1, 1, 2, 0, negative 2. And if you want to do this just for fun, try to do the other one where we put block identity behind it and row reduce all the way, and you will get, if I scalar multiply that in there, remember the 1/2 goes on to everybody. This gives me the matrix negative 1/2, 1/2, negative 1/2, negative 1/2, 1/2, 1/2, 1, 0, negative 1, which will be much less fun to find, you'll see when you try to do this using Gaussian elimination. But this is the inverse of the matrix. Please subscribe below. You'll get the notification for the rest of the videos in this series and a bunch of other ones. But for now, basically, this will be a bunch of questions that we're going to do for specifically for the COVID scenario for Math 120. I'll see you next time.